Hello everyone, I am Dr. Clament, Research Assistant Professor working at the Department of Chemistry, SRM Institute of Science and Technology, KTR campus. Today I will discuss Module 1, which is Introduction to Nanochemistry. When I say nano, I wish to introduce Richard Feynman, the first man who got excited about nano. And he was born in New York City, US, and he studied in MIT, that is Massachusetts Institute of Technology, and Princeton University. And he received Nobel Prize for Physics in the year 1965. And his famous lecture is entitled as "There is Plenty of Room at the Bottom." So he is the father of nano, and he contributed a lot in nanophysics and nanochemistry. Now, first let us try to understand the nanoscale, which is from angstrom to centimeter. And this slide gives you a clear overview about the nanoscale. Say for example, the atoms, which is in angstrom range, while the molecules is in nanometer range, and the DNA is in 10 nanometer range, while the virus falls in the range of 100 nanometer range, and bacteria is in micro range, and human hair is in micro, and a small ant is in mm. So this slide gives you an overview with an example illustrating or displaying the size of the stuffs. I hope you understand that how atoms are in angstrom range while the small ant is in mm range. See, this is very interesting example for nano effect. The microscope is very famous in Roman treasure from the AD 400. Why? This glass contains a gold-silver alloy nanoparticles which are distributed in such a way to make the glass look green in reflected light, but when light passes through the cup, it reveals a brilliant red. This is because of the nano effect. So this is very interesting example to understand the nano effect. Now let us try to understand the difference between molecule, nanoparticles and bulk materials one by one. Say for example, the constitution. Molecules are collection of atoms, while nanoparticles are collection of few molecules. But the bulk materials are collection of thousands of molecules. Now let us look at the size. Molecules are always in the range of 10 to the power minus 12 meter, which means lower than the nanoscale, whereas the nanoparticles are in the range of 100 nanometer, meaning 2 to 100 nanometer, whereas all the bulk materials are in the range of microns. Let us try to understand the geometrical structure. Molecules are well-defined structures by virtue, and the nanoparticles are also well-defined structures by nature, whereas the bulk materials, the geometrical structure of the bulk materials depends on the crystalline lattice. Now the most interesting thing is the physical properties, namely melting point, boiling point, etc. Say for example, gold sheet melts at 1064 degrees Celsius, while the gold nanoparticle melts at 300 degrees Celsius. This is the interesting difference to be noted when we move from bulk to nano. Now let us understand the surface area. See, the surface area of a molecule is not applicable because it varies. And when we go to the nanoparticles, the surface area is very high compared to the bulk materials. And you have to note here, when we reduce the size to the nano, the surface area extremely increases, which is highly beneficial for several kind of applications that I will discuss in the next module. So this slide gives you an overview to understand the difference between molecules, nanoparticles, and bulk materials. Now, this is yet another exciting example to understand the nano. Say, for example, gold in bulk state, how their properties are. The same gold, when you make it in nano range, how the properties are drastically changing. Let us go one by one. Bulk gold, they are indeed very lustrous, means they have a shiny surface when polished, and they are malleable, which means can be harmed, can be bent or rolled, or any desirable shape we can make it. And the bulk gold is ductile in nature. It means it can be drawn into wires, and typically they are yellow color when you see as a bulk mass, and very high densities, and they are electrically conductor, and it has a high melting point, which is like 1080 degrees Celsius, and very high tensile strength, and unaffected by air and most reagents. Now let us try to understand the gold. See, when we move from bulk to nano gold, you can see very interesting and exciting properties. Say, for example, the first property, they vary in appearance depending on the size and shape of the cluster. It means when you reduce the size from micro to nano, or from to nano, their appearance is going to drastically change. That is what it means. They are never gold in color. It means when you reduce the size, the color is going to change. You can see the example here. Very interesting to note that when you make gold nanoparticles in the range of 25 nanometer, it appears red color. Interestingly, when you make the same nanoparticles in the range of 50 nanometer, they are green in color. So that is why we cannot say nano gold always shows the same color. According to the size, the color changes. It means the optical property changes. And they are very good catalysts, as we all know. And very interesting to note, they are not metals but semiconductors. Here you can just look at the melting point. The bulk gold melts at 1080 degrees Celsius, whereas the nano gold melts at relatively low temperature, which starts from 940 degrees Celsius. Not limited to this. When you reduce the size further, the melting point also goes down. So there is no constant melting point for nano gold. Yeah, this is the most important slide. The important phenomena that occur at the nanoscale. So so far what we discussed is just an introduction about the nano. And now we are entering into the real concept. What are the phenomena that we can see at the nanoscale? When you prepare any nanostructures, any nanomaterial at the nanoscale, you can expect these phenomena, especially the surface area to volume ratio phenomena. So we will discuss one by one. So today in this module, I will cover surface area to volume ratio effect. The interesting thing is the surface area to volume ratio effect increases the surface area. So that we will discuss one by one. Yeah. What is surface area to volume ratio? At the nanoscale, the surface area to volume ratio becomes increasingly significant. As the size of the material decreases to the nanoscale, its surface area increases dramatically compared to its volume. This has several important effects on properties. Surface area measures how much exposed area in a solid has, which is always expressed in square units. Say, for example, let us try to understand the surface area to volume ratio effect mathematically with two examples, namely sphere and cube. I'll first explain this sphere. Yes. So this is mathematical calculation for surface area to volume ratio for a cube. As we all know, the surface area, which is the formula is A by V. V is equal to A cube and A is equal to A square. This is volume, this is area. Consider a cube with a side length of 10. See, this is a cube we are going to consider and the side length is 10. The volume of this cube is 1000 because volume V is equal to A cube. So instead of A, if we substitute 10 here, so 10 multiplied by 10 multiplied by 10 gives 1000, which means the volume is 1000. Now let us calculate the area. So the formula for area is A square, which is 10 times of 10 gives 100. So now we know what is volume, what is area, so that we can calculate the surface area to volume ratio, that is A by B. Yes, the surface area is 6 into 100, that is 600. See, you should understand there are 6 sides are there. That is why, see, for one side it is 100, for 6 side it is 600. So 600 by 1000 gives 0.6. Next, we repeat the above procedure for the cube with the side length of 5. You have to note we are reducing the side length from 10 to 5. That is very important. In this case, the volume is 125 because 5 times of 5 times of 5 gives 125 and the surface area is 6 multiplied by 5 into 5, which is 150. So the surface area volume ratio is equal to 150 by 125, that is 1.2. It is clear that when the size of the cube is cut in half, that is from 10 to 5, the value of surface area to volume ratio doubles. Look at this. Here it is 0.6 and here it is 1.2. So that is the most interesting thing we have identified from this calculation, that when we reduce the size, area increases. Next, we repeat the above procedure for cube with a side length of 1. See, in the first case, we assume the side length as 10. In the second case, we assume the side length as 5. In the third case, we assume the side length as 1, which means we are reducing the side length step by step. So in this case, the volume is 1 because 1 times of 1 times of 1 is 1 and the surface area is 6 times of 1 multiplied by 1, which is 6. Thus, the value of surface area to volume ratio is 6 by 1, that is 6. Very interesting. In the first case, the surface area to volume ratio is 0.6 and in the second case, the surface area to volume ratio is 1.2 and in the third case, the surface area to volume ratio is 6, which means when we reduce the size length 10 to 5, 5 to 1, the surface area to volume ratio respectively increases from 0.6 to 1.2 and 1.2 to 6. The surface area to volume ratio drastically increases. This is one of the main features of materials at the nanoscale. Yeah. Now let us try to make a graph out of this. In this case, we can make a formula. Say for example, the volume of the cube is S cube and the surface area of the side is S square. The surface area of the cube is 6S square because there are 6 sides, correct? No? Thus, we obtain a general formula of surface area to volume ratio for a cube when we divide the surface area by the volume is 6 by S. That is 6S square by S cube is equal to 6 by S. Thus, the surface area to volume ratio is equal to 6 by S for a cube of a side length S. So, see figure 1 for a plot of the side of the cube versus surface area. So, here based on the previous calculations, we clearly understand as the side length decreases, the surface area to volume ratio dramatically increases. That is the interesting aspects. Yeah. Now let us use the general formula. that is 6 by S. For a cube, the side length 100 nanometer. Let us calculate the value of surface area to volume ratio. Since S is equal to 100 nanometer, so 100 into 10 to the power minus 9 meter, that is equal to 1 into 10 to the power minus 7 meter. When we obtain the surface area to volume ratio, when we substitute this, the answer is 6 multiplied by 10 to the power 7 per meter. This value is, see, these many times extremely large. Very interesting. That is 6 million times. Let us see what happens to the value of surface area to volume ratio when the side length of the cube is reduced to 10 nanometer. That is S is equal to 10, which we can just convert the unit, that is 1 multiplied by 10 to the power minus 8 meter, so that we can calculate the surface area to volume ratio, and the value is now 60 million times larger than the previous value. It is very clear from these two examples that we can obtain extremely large surface area when we reduce the side length. Similarly, we can calculate the surface area to volume ratio for a sphere. So in this case, the volume formula is 4 by 3 pi r cube and the area formula is 4 by pi r square. Consider a sphere of a radius equal to 10. The volume of the sphere is 4 by 3 pi r cube, right? So that we can substitute 10. So when we substitute 10, and we will get 4188.79. When n is well-known constant of the circle, that is the ratio of the area of the circle to its perimeter, the surface area of the sphere is same, the formula 4 by 3 pi r cube, and we will get 1256.64. Thus, when we divide this 1256.65 by 4188.29, we get the value 0.3. That is the surface area to volume ratio when we apply these values. Let us repeat this above procedure for a sphere of a radius equal to 5. See, in case 1 it was assumed 10, in case 2 it is 5. Now we have to calculate the volume and area. Then only we will be able to calculate the surface area to volume ratio, isn't it? So the volume formula again same 4 by 3 pi r cube, and the area formula 4 by pi r square. Now substitute 5 here. When we substitute 5 here, and the answer is going to be 0.6. Thus clearly the value of surface area to volume ratio doubles when the radius of the sphere is reduced from 10 to 5. Similarly, when we reduce the radius to 1, that is case 3, we repeat the above procedure to a sphere radius equal to 1. Okay. The same formula, v is equal to 4 by 3 pi r cube and a is equal to 4 by pi r square. When we substitute, and the answer we get is going to be 3. Very interesting. In case 1, it is 0.3, the surface area to volume ratio, and in case 2, in case 2 it is 0.6, and in case 3 it is 3. So when we reduce the diameter, that is R value, the surface area to volume ratio dramatically increases. So same like previous case, we can find out the formula using the volume and area, and the final formula is going to be 3 by R. So we can use this formula to calculate for any cases. So here also, as the radius of the sphere decreases, the surface area to volume ratio increases. This is the graphical representation. Correct. So now it is very clear from the formula, that is surface area to volume ratio is equal to 3 by R, that when R becomes very small, the surface area to volume ratio becomes very large. As R approaches 0, the value of surface area to volume ratio approaches infinity. Thus, for an infinitely small sphere, the value of surface area becomes infinitely large. Let us look at some numerical example of spheres at a nanoscale. Say for example, for a sphere of radius 100 nanometers, let us calculate the value of surface area to volume. When we substitute R is equal to 100, and that in meter, which is 1 into 10 to the power minus 7 meter, so that we obtain the surface area to volume ratio, that is equal to 3 multiplied by 10 to the power 7 per meter. This value is 3 million times high. So let us see what happens when the surface area to volume ratio, when the radius of the sphere is reduced to 10 nanometer. So R is equal to 10 nanometer, which is 10 multiplied by 10 to the power minus 10 meter. That is 1 multiplied by 10 to the power minus 8 meter. So that the surface area to volume ratio is equal to 3 multiplied by 10 to the power 8 per meter. This value is 30 million times larger than the previous value. It is very clear from these two examples that we obtain extremely large value of surface area to volume ratio for a sphere at the nanoscale when we reduce the radius values. And the summary. The summary is very interesting. The surface area to volume ratio clearly increases the surface area, which means the surface area increases as the particle size decreases. So this is the conclusion. So whenever you prepare any kind of nanoparticles, any kind of nanostructures, try to understand that when you reduce the particle size, automatically the surface area will increase. You all know very well the surface area is very beneficial for any kind of catalysis applications. So when you prepare or when you work with nanostructures, make sure that you're reducing the size so that you can increase the surface area. So with this summary, thank you all for listening to this video.